Look up at the night sky, really look at it, and tell me what you see. A scattering of stars, maybe the faint glow of distant galaxies, or the occasional streak of a shooting star. But here's the thing, what you're seeing is just the tiniest fraction of what's actually out there. The universe is a place of endless mystery, a cosmic playground filled with phenomena that defy our understanding, challenge our science, and ignite our imagination. We've sent probes to the edges of our solar system, built telescopes that peer back in time, and yet with every answer we uncover, a dozen new questions emerge. That's the thrill of it. The universe doesn't give up its secrets easily. Today, we're diving into 25 of the most mind-bending mysteries the cosmos has to offer. From black holes that warp the fabric of reality to dark energy quietly tearing the universe apart, these aren't just puzzles for astrophysicists, they're stories that shape our very existence. Imagine standing on the shore of an ocean so vast you can't see the other side, knowing that every wave carries a secret, every current hides a revelation. That's what exploring these cosmic enigmas feels like, and the best part, some of these mysteries might never be solved in our lifetime, which only makes the journey more exhilarating. Think about it, we live on a tiny speck of rock orbiting an average star in one of billions of galaxies. Yet, we've somehow scratched together enough knowledge to ask the right questions. How do supermassive black holes grow so big? What lurks in the voids between galaxies? Why does 95% of the universe remain invisible to us? These aren't just scientific curiosities, they're chapters in the grand story of human curiosity. And that's what this video is all about. Not just listing facts, but stepping into the unknown together, feeling the awe of discovery, and maybe, just maybe, catching a glimpse of how strange and beautiful the cosmos truly is. So, buckle up, we're about to take a journey through the greatest unsolved riddles of space, and trust me, you won't want to look away. Let's start with the biggest cosmic elephant in the room, dark matter. Picture this, every galaxy we've ever observed spins so fast that the sheer gravity of its visible stars shouldn't be enough to hold it together. And yet, galaxies aren't flying apart. Something invisible, something that doesn't emit, absorb, or reflect light, is holding them together with an unseen grip. That something is dark matter, a cosmic ghost that makes up roughly 27% of the universe. Here's what makes it so baffling. We know it's there because of its gravitational pull, but we've never directly detected it. It doesn't interact with light or ordinary matter in any way we can measure, at least not yet. Think of it like walking into a pitch-black room and feeling an unseen presence tugging at you, rearranging the furniture, but no matter how hard you search, you can't find the source. That's the frustration and the fascination of dark matter. Scientists have spent decades chasing shadows, building detectors deep underground to shield them from cosmic noise. One of the most ambitious experiments is the LUXZPLIN project, a liquid xenon detector buried nearly a mile beneath the Earth, waiting for the faintest whisper of a dark matter particle bumping into an atom. So far, nothing definitive, but the search isn't just about proving its existence, it's about rewriting our understanding of reality. Because if dark matter is real and it's everywhere, then most of the universe isn't made of atoms, stars, or planets. It's made of something we don't even have a name for yet, and that's the real kicker. Dark matter isn't just hiding in the voids between galaxies. It's woven through the room you're sitting in right now, passing through your body like you're made of air. Billions of these particles could be streaming through you every second, and you'd never feel a thing. That's how little we know, yet without dark matter, galaxies wouldn't exist as we see them. The universe would look completely different. So whatever this mystery substance is, it's not just a cosmic footnote, it's the scaffolding of reality itself. And the day we finally crack its code, that's the day the universe gets a whole lot stranger. If dark matter is the universe's invisible scaffolding, then dark energy is its hidden engine, a force so baffling it makes galaxies flee from each other faster than gravity can pull them together. Here's the cosmic shocker. Not only is the universe expanding, but that expansion is accelerating, and no one knows why. Picture a balloon with dots drawn on its surface. As you inflate it, the dots move apart. Now imagine the balloon starts inflating faster and faster on its own, as if some unseen hand keeps pumping air into it. That's what dark energy is doing to our universe. It's as if space itself has a built-in repulsive force, stretching the cosmos apart at an ever-increasing rate. And here's the kicker: dark energy isn't just powerful, it makes up a staggering 68% of the universe's total energy. That's more than dark matter and ordinary matter combined. The discovery of this acceleration in the late 1990s was so unexpected it won the Nobel Prize. Astronomers studying distant supernova assumed they'd find the universe's expansion slowing down due to gravity's pull. Instead, they saw the opposite. It was like tossing a ball into the air and watching it shoot upward faster and faster, defying gravity itself. That's the enigma of dark energy. It's not just winning against gravity, it's rewriting the rules of cosmic evolution. One of the most unsettling theories about dark energy's end game is the Big Rip. Imagine dark energy growing stronger over time, eventually overpowering not just galaxies but stars, planets, and even atoms. First, galaxies would be torn apart, then solar systems. Then, in the final moments, the very fabric of matter itself would unravel. It's a scenario where space-time doesn't just expand, it shatters. Of course, this wouldn't happen for billions of years, but the fact that it's even possible tells us how little we understand the force driving our universe. So what is dark energy? The leading guess is something called vacuum energy, a property of empty space itself. According to quantum physics, even a perfect vacuum isn't truly empty. It's a seething foam of particles popping in and out of existence. This quantum frenzy might be generating a repulsive force, but here's the problem. When physicists calculate how strong this effect should be, their numbers are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's the worst prediction in the history of science. The other possibility, Einstein's greatest blunder, might have been right after all. He once proposed a cosmological constant, a built-in energy of space that could explain a static universe. He later abandoned the idea, but now it's back in play as a potential explanation for dark energy. Or maybe it's something entirely new, a fundamental force we haven't discovered yet. Whatever the answer, one thing's clear: dark energy isn't just a mystery. It's the force that will determine the ultimate fate of everything, and right now, it's laughing in the face of gravity. Now, let's shift our gaze to something even more unsettling: a gravitational monster lurking in the cosmic shadows, pulling entire galaxies toward it like a cosmic riptide. Meet the Great Attractor, a mysterious region of space with the mass of tens of thousands of Milky Ways, bending the paths of galaxies across our local universe. But here's what makes it so eerie: we can't actually see it. Our own galaxy's thick disk of stars, gas, and dust, what astronomers call the zone of avoidance, blocks our direct view, like trying to peer through a dense fog. For decades, this region was a blind spot, hiding whatever colossal structure was yanking galaxies off course. Imagine feeling a powerful current tugging your boat, but every time you try to look for the source, a massive wave obscures your view. That's the frustration scientists faced until X-ray telescopes cracked the cosmic curtain. Recent breakthroughs with instruments like the Chandra X-ray Observatory and the European Space Agency's XMM Newton have pierced through the zone of avoidance, revealing clusters of galaxies so massive their gravity distorts spacetime itself. The leading theory: the Great Attractor isn't a single object but a dense knot in the cosmic web, a supercluster of galaxies, dark matter, and superheated gas, acting as a gravitational anchor for our galactic neighborhood. But the plot thickens. Even this supercluster might not be the final answer. Observations suggest something even larger. The Shapley supercluster, over 600 million light-years away, could be pulling both the Great Attractor and us toward it. It's like discovering the current dragging your boat isn't just from a nearby whirlpool, but from a distant, monstrous waterfall. The scale of this motion is staggering. Our Milky Way, along with hundreds of other galaxies, is racing toward the Great Attractor at over 14 million miles per hour. And yet, because the universe itself is expanding, we'll never actually reach it. It's a chase where the finish line keeps moving, a cosmic game of tug-of-war between gravity and dark energy. What's truly humbling is realizing this isn't just about distant galaxies. The Great Attractor's pull shapes the fate of everything in our corner of the cosmos, including us. Every star, every planet, every atom in your body is caught in this vast, invisible flow. And the deeper we look, the more we realize the universe isn't just expanding, it's alive with motion, a dance of forces we're only beginning to understand. Deep in the vast silence of space, something occasionally screams, a blast of radio waves so powerful it outshines entire galaxies, lasting just 1,000th of a second before vanishing without a trace. These are fast radio bursts, or FRBs, and they're one of the universe's most electrifying puzzles. Imagine sitting in a quiet forest when, out of nowhere, a single thunderclap shakes the trees, then silence returns as if nothing happened. Now imagine that thunderclap came from billions of light-years away, carrying more energy than the sun emits in 80 years. That's the enigma of FRBs. For over a decade, astronomers scratched their heads over these fleeting signals. Were they collisions between neutron stars, the death throes of black holes? Or, as some dared to whisper, though with a chuckle, aliens? The first FRB was spotted in 2007, buried in old radio telescope data, and for years it seemed like a cosmic fluke. Then more were found, each one a blip of radio static from a different corner of the universe, each leaving behind more questions than answers. Enter the CHIME telescope, a game-changer in the hunt for these radio ghosts. Unlike traditional dish telescopes, CHIME is a sprawling array of metal cylinders in a Canadian field, designed to scan huge swaths of sky at once. It's like trading a magnifying glass for a floodlight, and the results have been staggering. Since its launch in 2018, CHIME has detected hundreds of FRBs, including something revolutionary, repeating bursts. That's right, some of these cosmic screams aren't one-offs. They're recurring, like a lighthouse beam flickering across the universe. One of the most famous repeaters, FRB 121811, has become a Rosetta Stone for astronomers. By tracing its echoes through interstellar gas, scientists pinpointed its home galaxy, a messy, turbulent dwarf galaxy over 1.5 billion light-years away. That location offers a crucial clue. These bursts thrive in chaotic environments where young neutron stars, or magnetars, neutron stars with magnetic fields 1 trillion times stronger than Earth's, might be lurking. Picture a magnetar quake, a starquake so violent it rips open the star's crust, unleashing a magnetic shockwave that lights up the radio sky. That could explain some burst. But here's where it gets wild. In 2020, astronomers caught an FRB inside our own galaxy, linked definitively to a magnetar, finally a smoking gun. Except not all FRBs fit this mold. Some are too energetic, too unpredictable. Could there be multiple cosmic factories churning out these signals? And why do a handful repeat while most vanish forever? The alien hypothesis, though tantalizing, remains the least likely answer, but the mere possibility speaks to how baffling FRBs are. When a signal from deep space defies explanation, even scientists entertain wild ideas. What's certain is this: every new burst peels back another layer of the mystery, revealing a universe far louder and more mysterious than we ever imagined. And with telescopes like CHIME listening, we might finally be closing in on the truth 1 millisecond scream at a time. In a universe so vast it boggles the mind, with hundreds of billions of galaxies, each containing hundreds of billions of stars, there's one question that keeps creeping into the silence: where is everyone? This is the Fermi Paradox, the glaring contradiction between the high probability of alien civilizations and the utter lack of evidence for their existence. We've been shouting into the cosmic void for decades, sending radio signals, launching probes, scanning the skies for even a whisper of reply, and so far, nothing but static. The paradox gets its name from physicist Enrico Fermi, who famously asked during a lunchtime conversation in 1950, "If they're out there, why haven't we seen them?" Think about it, our galaxy alone is over 13 billion years old. Even if intelligent life evolved on just a handful of planets, some of those civilizations should have had more than enough time to spread across the stars. So why does the universe feel so empty? This is where the great filters come in, theoretical barriers that might prevent life from progressing beyond a certain point. Some filters could lie in our past, like the improbable leap from simple chemistry to self-replicating life. Others might loom ahead, waiting to wipe out civilizations before they can colonize the galaxy: nuclear war, runaway AI, or environmental collapse. The chilling possibility: we might be alone not because life is rare, but because intelligence is a dead end. Then there's Drake's equation, the famous formula that tries to estimate the number of communicative civilizations in our galaxy. Plug in optimistic numbers, plenty of habitable planets, high odds of life emerging, and you get thousands of alien societies. But here's the catch: every variable is a guess. We don't know how many planets develop life, how often life becomes intelligent, or how long civilizations last before vanishing. The equation isn't an answer, it's a mirror reflecting just how little we know. And then there's Oumuamua, the first known interstellar visitor to pass through our solar system. This bizarre, tumbling object, spotted in 2017, defied easy explanation. Its elongated shape, unusual acceleration, and lack of a visible comet tail sparked wild speculation. Harvard astronomer Avi Loeb famously suggested it could be artificial, a solar sail or probe from another civilization. Most scientists lean toward natural explanations, like outgassing hydrogen, but the truth is, we'll never know for sure. Oumuamua is already gone, racing toward the outer solar system, leaving behind nothing but questions. That's the haunting beauty of the Fermi Paradox. It's not just about aliens, it's about us. Are we the first, the last, or is the universe hiding something even stranger? Every silent radio telescope, every empty patch of sky, whispers the same unsettling thought: the cosmos might be far lonelier than we ever imagined. Or worse, we might be missing the signs right in front of us. On the night of August 15, 1977, a radio telescope in Ohio picked up a signal so unusual that the astronomer who discovered it scrawled, "Wow," in red ink right on the printout. This wasn't just background static or some known cosmic phenomenon. It was a narrowband radio burst, the exact type of signal scientists had predicted an alien civilization might use to announce its existence. For 72 electrifying seconds, the signal blared at 50 times the noise of deep space, perfectly matching the expected frequency of hydrogen, the most common element in the universe. Then, just as suddenly as it appeared, it vanished, never to be heard again. The wow signal originated from the direction of the constellation Sagittarius, near a star system called Chi Sagittarii, roughly 200 light-years away. What made it so tantalizing wasn't just its strength or frequency, but its structure. Natural cosmic radio sources, like pulsars or quasars, typically emit across a broad range of frequencies. This was surgically precise, like a laser beam cutting through the noise. It even exhibited a slight drift in frequency, just as you'd expect from a signal originating on a rotating planet. The more scientists analyzed it, the harder it became to dismiss as anything but deliberate. Of course, the universe loves throwing curveballs, and astronomers scrambled to find natural explanations. Could it have been a passing comet? In 2017, one researcher suggested hydrogen clouds around comets might produce such emissions, but the dates didn't align. No known comets were in that region of space when the signal arrived. What about a rogue satellite or military transmission? Highly unlikely. The frequency used 1420 MHz is protected worldwide as a quiet band reserved exclusively for astronomy. Even today, no human technology is known to produce such an emission pattern at that intensity. The real frustration is that despite decades of follow-up scans, including a comprehensive 2-year hunt by the Very Large Array in 2020, the signal never repeated. SETI modern efforts now focus on the Taurus constellation, where similar narrowband anomalies have occasionally flickered into existence. Projects like Breakthrough listen deploy machine learning to sift through millions of radio channels, hoping to catch another wow moment. But here's the haunting thought. If that 72-second burst was a beacon, it might have been aimed deliberately, a fleeting hello from a civilization that's long since turned its attention elsewhere. Or maybe, just maybe, we're not listening the right way. The WOW signal lives on as both inspiration and cautionary tale. It reminds us that the universe could be shouting in a language we're only beginning to decipher, and the next time we hear it, we'd better be ready to answer. Some stars flicker gently as planets pass in front of them, a predictable, rhythmic dimming astronomers have seen thousands of times, but then there's Tabby star. Officially named KIC 8462852, this bizarre flickering sun defies every expectation, dimming unpredictably by up to 22%, as if something colossal and jagged is passing in front of it, blocking its light in ways no natural phenomenon should. When astronomer Tabitha Boyajian first spotted these erratic dips in 2015, the data was so strange her team nicknamed it the WTF star, and the theories. They range from cosmic dust to something far more speculative, alien megastructures. At first glance, Tabby's star looks ordinary, a yellow-white dwarf about 1,500 light-years away in the constellation Cygnus. But ordinary stars don't behave like this. Imagine watching a porch light that normally shines steadily, except sometimes it flickers like a candle in the wind, dimming for days or weeks before brightening again with no discernible pattern. That's what telescopes like Kepler observed. The dips weren't smooth like a planet's transit. They were jagged, asymmetrical, as if something with irregular edges, a swarm of broken comets perhaps, was drifting haphazardly across the star's face. The most tantalizing hypothesis came from Penn State astronomer Jason Wright, who suggested the dips might match what we'd expect from a Dyson swarm, a hypothetical cloud of energy harvesting megastructures built by an advanced civilization. Picture millions of solar panels or habitats orbiting a star, absorbing its light. The idea sent shockwaves through the scientific community, not because it was likely, but because for the first time we had data strange enough to warrant considering it. But science thrives on ruling out the extraordinary, and by 2023, the megastructure theory began crumbling under the weight of new evidence. Detailed spectral analysis revealed the star's light was being filtered through vast clouds of carbon-rich dust particles finer than cigarette smoke. When Tabby's star dimmed, its infrared emissions spiked, a telltale sign of dust absorbing and re-radiating light. No solid megastructure would behave this way. Instead, astronomers now suspect a messy, chaotic debris field, maybe the remnants of a shattered planet or a colossal collision between asteroids, is casting these eerie shadows. Yet even this explanation leaves gaps. Why does the dust appear in irregular clumps? What catastrophic event could have created so much debris, and why does the star's long-term dimming, a separate mystery, suggest it's gradually fading over centuries? The most compelling theory points to a traumatized solar system where a destabilized exoplanet or a rogue star's gravitational pull triggered a cascade of collisions, leaving behind a haunting veil of dust. Tabby's star remains a testament to how little we truly understand about cosmic oddities. It's a reminder that the universe doesn't need aliens to be weird. It's perfectly capable of cooking up mysteries all on its own. And as new telescopes like the James Webb Space Telescope turn their gaze toward this stellar enigma, one thing's certain: the answers, when they come, will be stranger than fiction. At the centers of some of the universe's most violent galaxies, cosmic monsters are hard at work. Supermassive black holes so voracious they outshine every star around them. These are quasars, the brightest objects in existence, capable of blasting out energy equivalent to 1,000 Milky Ways from a region no larger than our solar system. Picture a spotlight so intense it could be seen from the edge of the observable universe, powered by nothing more than a gravitational abyss. The secret to a quasar's power lies in its insatiable appetite. As gas, dust, and even entire stars spiral toward the black hole at its core, friction heats this material to millions of degrees, creating a swirling disk of plasma that glows brighter than anything else in nature. But here's the twist: not all of this doomed matter actually crosses the event horizon. Some gets funneled into jets of particles shot outward at nearly light speed, carving through space like cosmic blowtorches. These jets can stretch for millions of light years, sculpting the galaxies around them and seeding the universe with heavy elements. Quasars were more common in the early universe, when galaxies were gas-rich and chaotic. Today, most have gone quiet, their black holes starved of fuel. But when we look at distant galaxies, their light traveling billions of years to reach us, we're essentially looking back in time, witnessing these titans in their prime. The brightest quasar ever discovered, J2157, shines with the luminosity of 66 trillion suns. To put that in perspective, if it sat where our sun is, its radiation would vaporize Earth in seconds. Yet quasars aren't just relics of the past. Their quieter descendants still shape galaxies today, including our own. The Milky Way's central black hole, Sagittarius A star, is a sleeping giant. But give it a fresh meal, say, a wandering gas cloud or a careless star, and it could flare up, reminding us that even dormant monsters can wake. Now, let's talk about how galaxies grow, not just by making stars, but by devouring their neighbors. Take Andromeda, our closest galactic sibling. It might look serene from a distance, but this spiral beauty is a cannibal. Over billions of years, Andromeda has ripped apart and absorbed dozens of smaller galaxies, leaving behind ghostly trails of stars as evidence. This isn't some rare cosmic crime, it's how galaxies evolve. When two galaxies collide, their stars rarely crash together. Space is too vast. Instead, their mutual gravity twists them into bizarre shapes, funneling gas toward their central black holes and triggering new star formation. The Milky Way is no saint either. We've consumed at least a dozen smaller galaxies, including one just discovered in 2022. A victim so thoroughly digested its stars now swirl anonymously among ours. But the real feast is yet to come. In about 4 billion years, Andromeda and the Milky Way will merge in a slow-motion dance, their black holes eventually spiraling together in a gravitational wave, generating tango. The result, a new hybrid galaxy some astronomers call Milkdromeda. It's a reminder that the cosmos isn't static. It's a battlefield of creation and destruction, where even the mightiest galaxies are both predators and prey. What's fascinating is how these two mysteries, quasars and galactic cannibalism, are connected. A galaxy merger can funnel fresh gas to a dormant black hole, reigniting it as a quasar. In turn, that quasar's jets heat up surrounding gas, shutting off star formation and effectively sterilizing its host galaxy. It's a cosmic feedback loop. Violence begets violence, and the universe keeps its own brutal ledger. So next time you gaze at a peaceful night sky, remember, Behind that tranquility lies a history of collisions, feasts, and resurrected monsters. The universe doesn't do quiet, it does transformation. And we're just along for the ride. The moon seems like a quiet neighbor today, a pale, airless world with no magnetic field to shield it from the solar wind. But pick up a lunar rock brought back by the Apollo astronauts, and you're holding a clue to a far more dynamic past. Some of these ancient samples bear traces of magnetism, as if they solidified in the presence of a global magnetic field. That shouldn't be possible. Small, rocky worlds like our moon cool quickly, their cores solidifying within a billion years, far too soon to sustain the churning molten metal needed to generate a planetary magnetic dynamo. So how did the moon, just 1% of Earth's mass, once have a magnetic field rivaling our own? The answer might lie in a forgotten chapter of lunar history when the moon's core was still alive with motion. One leading theory suggests that tidal forces from a much closer Earth, stretching and squeezing the young moon like cosmic putty, kept its core molten far longer than physics would normally allow. Picture a ball of hot iron wrapped in a blanket of rock, constantly kneaded by Earth's gravity until it began to swirl, generating a magnetic shield that lasted for nearly a billion years. But then, as the moon drifted outward, the tidal heating faded, the dynamo sputtered, and the field collapsed, leaving behind only magnetized rocks as cryptic tombstones. Not everyone's convinced, though. Some scientists argue the magnetism could be contamination from Earth's field or even from shock waves of ancient asteroid impact. That's when NASA Artemis missions come in. Future lunar landers won't just scratch the surface, they'll drill deep, extracting core samples from regions like the moon's south pole, where untouched layers of crust might preserve a clearer record of this magnetic mystery. Imagine pulling up a cylinder of rock that's been sealed away for 4 billion years, its minerals frozen in time like a cosmic tape recorder. But here's the twist: if the moon did have a magnetic field, it changes everything we thought we knew about its early environment. A magnetic shield would have deflected solar radiation, potentially preserving pockets of water ice in shadowed craters far earlier than we assumed. It might even have sheltered any primitive chemistry bubbling away in temporary lunar ponds, raising the faintest possibility that the moon, however briefly, flirted with conditions ripe for life. That's the thrill of this mystery. The moon isn't just a dead rock. It's a fossilized time capsule hiding chapters of its youth in plain sight. And with Artemis poised to rewrite the story, one drill sample at a time, we might soon learn that our nearest celestial neighbor was once a world of fire, motion, and maybe, just maybe, a flicker of cosmic magic. Venus has long been Earth's evil twin, a world of crushing pressure, scorching surface temperatures hot enough to melt lead, and skies choked with sulfuric acid. But in 2020, this hellish planet threw scientists a curveball: traces of phosphine gas floating in its upper clouds. On Earth, phosphine is almost exclusively produced by living organisms, anaerobic microbes thriving in oxygen-free environments like swamps or penguin guts. So when astronomers detected this fingerprint of potential life 60 kilometers above Venus's surface, the implications were explosive. Could there be microorganisms floating in Venus's temperate cloud layers, surviving where no human probe could? The discovery sparked instant controversy. Some researchers argued the phosphine signal might be a false alarm, a misreading of sulfur dioxide, a common Venusian gas with a similar spectral signature. Others countered that even if it was phosphine, abiotic processes like volcanic activity or lightning might explain its presence. But here's the catch: Venus's volcanoes don't seem to be erupting enough to produce such quantities, and lightning alone can't account for the gas's persistence. That leaves a tantalizing, if improbable, possibility: microbial life drifting in the clouds, building tiny ecosystems inside acidic droplets. This wouldn't be the first time scientists imagined life in such hostile skies. Back in the 1960s, Carl Sagan speculated about Venusian floaters, balloon-like organisms riding the planet's wind currents. Modern models suggest more plausible microbes, perhaps armored against acidity like Earth's extremophiles, metabolizing sulfur and exhaling phosphine as a byproduct. Picture a planet where life didn't cling to the surface but retreated upward, finding refuge in the only habitable zone left, a narrow band of clouds where temperatures and pressures eerily resemble Earth's. Enter DAVINCI, NASA upcoming mission to crack Venus's mysteries. Slated for launch in 2029, this probe will plunge through the atmosphere, sniffing for phosphine and mapping its distribution like a cosmic detective. Unlike previous missions, DAVINCI's instruments are fine-tuned to distinguish phosphine from imposters, settling the debate once and for all. But the probe's real power lies in its ability to sample Venus's cloud chemistry in unprecedented detail, analyzing not just gases but the size and composition of cloud droplets themselves. If there's life there, it won't hide for long. What makes this mystery so thrilling is the sheer audacity of the idea. Venus's surface is a furnace, its atmosphere a corrosive nightmare, yet life might have found a way. And if it did, the implications are universe-shaking. Life isn't a rare fluke confined to Goldilocks zones, but a relentless force, adapting to even the most infernal corners of the cosmos. Until DAVINCI delivers its verdict, Venus's skies remain the ultimate cosmic Rorschach test, a swirl of acid and gas where some see chemistry and others just maybe see ghosts. Mars has always been the planet of almost Earth-like, almost habitable, almost within our reach. But one discovery has scientists leaning forward in their seats: methane, a gas that shouldn't flicker in and out of the Martian atmosphere the way it does. The Curiosity rover has been sniffing this out since landing in 2012, and what it's found is baffling. Methane levels that spike unpredictably, sometimes soaring to 10 times background levels before vanishing without a trace. On Earth, methane is a calling card of life, produced by everything from bacteria to cow digestion. But Mars doesn't have cows or obvious bacteria, so what's pumping this gas into the thin Martian air? The first clue lies in timing. Curiosity's readings show methane concentrations follow a seasonal cycle, peaking in late summer and fading in winter. That's a pattern that could hint at microbial activity. If subterranean organisms were metabolizing beneath the surface, their output might wax and wane with temperature changes. But there's a catch. Methane should stick around for centuries in Mars's stable atmosphere. The fact that it disappears so quickly suggests something or someone is breaking it down. UV radiation from the sun plays a role, but not fast enough to explain the rover's observations. Could unseen chemistry in the Martian soil be scrubbing the gas away? Or is there a more tantalizing explanation, that living organisms are both producing and consuming it? Not so fast, say geologists. Mars is a world sculpted by volcanoes, even if they've been dormant for millions of years. Serpentinization, a reaction between water, rock, and heat, could generate methane without any biology required. Imagine groundwater seeping through olivine-rich crust, sparking a chemical chain reaction that exhales methane as a byproduct. It's a compelling theory, except for one hiccup. No active volcanic hotspots or recent lava flows have been found to power such reactions. Enter the Rosalind Franklin rover, the European Space Agency's answer to this cosmic whodunit. Slated to land in 2028, ExoMars will carry a drill capable of burrowing 2 meters beneath the surface, deep enough to reach where radiation hasn't sterilized potential organic material. Its onboard lab won't just detect methane, it'll analyze carbon isotopes within the gas. Life on Earth prefers lighter carbon-12 over heavier carbon-13. If Martian methane shows that same bias, it'll be the closest thing to a smoking gun we've ever had. But here's the eerie part. Even if the answer turns out to be geological, Mars is whispering that it's more dynamic than we thought. Those methane spikes hint at hidden reservoirs, underground water, or energy sources we haven't mapped. The universe has a way of teasing us, dangling the possibility of life while keeping the truth just out of reach. And that's what makes this mystery so thrilling. Whether the culprit is biology or geology, Mars isn't the dead world we once assumed. It's a puzzle box waiting for Rosalind Franklin, or maybe the next rover or the one after that, to crack it open. Beneath Europa's frozen crust lies perhaps the most tantalizing secret in our solar system, a vast global ocean with more liquid water than all of Earth's seas combined. This isn't just a puddle trapped under ice. It's a churning, salty abyss kept warm by the relentless gravitational kneading of Jupiter and its moons. And in 2014, the Hubble Space Telescope caught this hidden ocean, literally spilling its guts, gigantic plumes of water vapor erupting over 100 miles into space like geysers shouting, "Come and find us." What makes Europa's ocean so special isn't just its existence, it's the ingredients for life. On Earth, wherever we find liquid water, energy, and organic molecules, life finds a way. Hydrothermal vents at the bottom of our oceans host entire ecosystems thriving in total darkness, fueled by chemical reactions rather than sunlight. Europa could have the same recipe. Its ocean floor is likely dotted with volcanic vents, simmering with heat from the moon's molten core. Add in organic compounds delivered by comet impacts, and you've got a cosmic laboratory primed for biology. But how do you study an ocean locked under 10 to 15 miles of ice? That's where NASA Europa Clipper comes in. Launching in 2024, this spacecraft won't land, it'll perform 45 high-risk flybys, skimming as close as 16 miles above Europa's fractured surface. Its suite of instruments will act like a Swiss Army knife for alien ocean hunting. Ice-penetrating radar to map the subsurface, thermal imagers to spot fresh eruptions, and most crucially, a mass spectrometer to taste those plumes. If Europa's jets contain amino acids, lipids, or even molecular hydrogen, Clipper will know. The real challenge, distinguishing between chemistry and biology. Say Clipper detects complex organics, how do we tell if they're from living processes or just abiotic reactions? That's why scientists are obsessed with the moon's chaotic terrain. Regions called chaos terrains, where ice has collapsed and refrozen, could be direct windows into the ocean below. If Clipper finds fresh, mineral-rich ice near these areas, it might mean the ocean is actively mixing with the surface, delivering its secrets upward. Then there's the wild card, Europa's ionosphere. In 2016, Hubble spotted what looked like auroras dancing over the moon's southern pole. But unlike Earth's auroras, these weren't caused by solar wind. They suggested Europa's plumes are ionizing, creating a temporary atmosphere. Clipper will measure this phenomenon in real time, offering clues about how often eruptions occur and how much material they're spewing. The stakes couldn't be higher. If Europa's ocean is habitable, or worse, inhabited, it rewrites our understanding of life's tenacity. Imagine microbes evolving not just in warm tidal pools, but in the lightless depths of an icebound alien sea, surviving on chemical energy for billions of years. It would mean life isn't a planetary accident, but a cosmic imperative, bubbling up wherever conditions are barely tolerable, and Europa's greatest trick. Its ocean has been there since the solar system's infancy. If life got started early, it's had more time to evolve than we've had on Earth. That's the thrill of this mystery. We're not just exploring a moon, we're probing the boundary between solitude and ubiquity, wondering if biology is a fluke or a franchise. And with Clipper's launch just around the corner, we might be on the verge of answering humanity's oldest question. Are we alone, or has Europa been hiding neighbors all along? Saturn's moon Titan doesn't just resemble Earth, it feels like a twisted mirror version of our planet, where familiar landscapes are remade with alien ingredients. Picture rivers carving valleys, but instead of water, they're liquid methane. Envision dunes stretching for miles, but composed not of sand, but of plastic-like hydrocarbons. And looming over it all, a hazy orange sky where organic molecules rain down like snowflakes. This isn't just another icy moon. Titan is a chemistry lab the size of a world, simmering with the same carbon-rich compounds that kick-started life on Earth. What makes Titan so electrifying is its sheer abundance of probiotic ingredients. The Cassini probe, which orbited Saturn from 2004 to 2017, revealed a surface dotted with methane lakes, some as deep as the Great Lakes, and vast oceans of ethane lurking beneath the crust. But the real gold mine, the atmosphere, Titan's skies are a factory for complex organics, where sunlight splits nitrogen and methane molecules, triggering chain reactions that create everything from vinyl cyanide to benzene. These molecules drift downward, coating the surface in a sticky film of potential. Here's where it gets wild. On Earth, similar compounds dissolved in ancient seas may have formed the first cell membranes. Titan's methane lakes could be doing the same thing, just at temperatures close to -180 degrees Celsius. That's the premise behind NASA's Dragonfly mission, a nuclear-powered drone set to land in 2034. Unlike rovers, Dragonfly will hop across Titan's surface, sampling dunes and dry lakebeds with a mass spectrometer capable of detecting amino acids or even lipids. The goal, to find out if Titan's chemistry is just a snapshot of early Earth, or if it's cooking up something even stranger. But life as we know it isn't the only possibility. Titan's methane cycle mirrors Earth's water cycle, complete with evaporation, rain, and erosion. Could there be microbes breathing hydrogen instead of oxygen, metabolizing acetylene instead of glucose? Lab experiments show Earth bacteria can survive in Titan-like conditions, hinting that life might not need liquid water, just a solvent, any solvent, to shuttle molecules around. Methane might be Titan's water equivalent, with cell membranes made of acrylonitrile, a compound Cassini detected in the Moon's atmosphere. The stakes are cosmic. If Dragonfly finds even hints of molecular complexity beyond what's possible through abiotic chemistry, it would prove that life's building blocks form readily across the universe. And if, against all odds, it stumbles upon something truly alive, Titan would become ground zero for the most revolutionary discovery in human history, proof that life isn't a one-time miracle, but a cosmic inevitability, adapting to whatever conditions it finds. Until then, Titan remains a frozen time capsule holding secrets older than life itself. It's a reminder that the universe doesn't play by our rules, it invents new ones in places we're only beginning to explore. Beyond Neptune's orbit, where sunlight is barely a glimmer, lies a frozen graveyard of cosmic leftovers, the Oort cloud. This vast spherical shell of icy debris stretches nearly a light year from the Sun, a relic of the solar system's violent infancy. Imagine trillions of comets, some as small as houses, others dwarfing mountains, all drifting in a deep freeze so distant they take millennia to complete a single orbit. These aren't just space rocks, they're time capsules, preserving the primordial ice and dust that built our planets billions of years ago. Yet for all its theoretical grandeur, the Oort cloud remains one of astronomy's great ghost stories. We've never seen it directly. Its existence is inferred from the rare comets that get nudged inward, like celestial breadcrumbs leading back to an invisible pantry. The most famous of these visitors, long-period comets like Hale-Bopp, which swing by Earth once every few thousand years after being dislodged from their icy slumber. Their elongated orbits point like arrows to the Oort cloud's presence. But here's the twist, some of these orbits are too stretched, too oddly clustered, as if something massive, something unseen, is herding them. That's where Planet 9 enters the picture. Hypothesized in 2016, this potential super-Earth, 5 to 10 times our planet's mass, could explain the peculiar orbits of distant objects like Sedna and Biden. Picture a hidden puppeteer lurking in the solar system's backyard. its gravity sculpting the paths of icy bodies over eons. The hunt for Planet 9 is like searching for a black cat in a coal cellar. Current telescopes can only spot it if it's reflecting enough sunlight, and at that distance, even a giant planet would be dimmer than the faintest star. But hope is on the horizon. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST, will scan the entire southern sky every few nights starting in 2025. With its 3200 megapixel camera, it could catch Planet 9's slow crawl against the stars, or something even stranger, because the Oort cloud isn't just home to native comets. Interstellar interlopers like Oumuamua and Borisov suggest our solar system's outskirts are a bustling crossroads for wandering objects. The LSST might spot dozens more of these visitors, each one a scrapbook page from another star system. Some could even be ejected exoplanets, rogue worlds flung into the void by gravitational chaos. What's truly humbling is realizing the Oort cloud isn't unique. Every star likely has one, meaning the galaxy is laced with overlapping shells of icy debris, a hidden architecture we're only beginning to map, and if Planet 9 is real. It's a reminder that our solar system's story isn't finished. There are still chapters waiting to be written in ink we haven't yet seen. In the vast emptiness of space, where the laws of physics are supposed to behave with clockwork precision, two tiny spacecraft defied expectations, Pioneer 10 and Pioneer 11. Launched in the early 1970s, these trailblazing probes were the first to venture past the asteroid belt, the first to visit Jupiter and Saturn, and the first human-made objects destined to leave our solar system entirely. But as they raced toward interstellar space, something peculiar happened. Both probes began slowing down more than they should have, as if an invisible hand were gently tugging them backward. This tiny deviation, just a fraction of a nanometer per second squared, became known as the Pioneer Anomaly, and for decades it haunted physicists like an unsolved equation. At first glance, the slowdown seemed trivial, but in the precise world of orbital mechanics, even the slightest unexplained acceleration is a red flag. Pioneer 10 hurtling toward Aldebaran and Pioneer 11 arcing toward the constellation Aquila both experienced the same mysterious deceleration. The probes weren't veering off course, they were just a little slower than every calculation predicted. Scientists scrambled for explanations. Was it friction from interplanetary dust? The gravitational pull of unseen dark matter? Or was it something deeper, a flaw in our understanding of gravity itself? For years, thermal radiation became the prime suspect. The probe's radioactive power sources emitted heat, and if that heat radiated unevenly off the spacecraft surfaces, it could, in theory, create a tiny thrust in the opposite direction. Meticulous reconstructions of Pioneer's design seem to support this, but here's the catch. When researchers crunched the numbers, thermal radiation could only account for about a third of the observed anomaly. The rest remained stubbornly unexplained. The mystery took an even stranger turn when similar anomalies popped up elsewhere. The Galileo spacecraft orbiting Jupiter and the Ulysses probe studying the Sun's poles showed hints of the same behavior. Even New Horizons, the mission that flew past Pluto, carried instruments designed to check for the Pioneer effect, though its trajectory hasn't yet revealed a clear deviation. These echoes of the anomaly suggest that if thermal radiation isn't the full answer, there might be something fundamental we're missing. Enter the realm of speculative physics. Some theorists propose modifications to Einstein's general relativity, tiny tweaks to how gravity behaves over vast distances. Others wonder if dark energy, the force accelerating the universe's expansion, could have local effects we don't yet understand. Then there's the most tantalizing idea of all, that the Pioneer Anomaly is a glimpse of entirely new physics, a gravitational quirk that only reveals itself in the deep, quiet stretches between stars. Yet with no active Pioneer-like missions currently headed outward, the anomaly remains frozen in time, an unsolved riddle drifting in the void. Perhaps one day a future probe designed specifically to test this mystery will finally crack it. Until then, the Pioneer's unexpected slowdown stands as a quiet reminder. Even in the emptiness of space, the universe still has secrets it isn't ready to share. If you took the universe's temperature, you'd find it's not perfectly even, not by a long shot. Tiny variations in the cosmic microwave background, or CMB, the afterglow of the Big Bang, reveal where matter was slightly denser or hotter in the infant cosmos. These fluctuations should be random, like static on an old TV screen. But when scientists mapped them, they found something unsettling. A bizarre alignment along a single axis, as if the universe had a built-in preference. Astronomers call this the axis of evil, not because it's malevolent, but because it defies everything we thought we knew about cosmic randomness. This axis isn't just a minor statistical quirk. The CMB's hot and cold spots appear to line up in a way that points roughly toward the constellations Leo and Virgo, with a second, perpendicular axis stretching toward Aquarius. According to standard cosmology, these patterns should be as directionless as a splatter of paint. Yet here they are, whispering that the universe might have a hidden structure, or worse, that our models of cosmic inflation could be missing a critical piece. One theory suggests that gravitational waves from the Big Bang itself might have imprinted this alignment, like fingerprints on spacetime. Others propose that we're seeing the gravitational tug of a neighboring universe beyond our cosmic horizon, warping our infant cosmos like a reflection in a funhouse mirror. Then there's the uncomfortable possibility that the axis isn't cosmic at all, just an artifact of measurement errors or foreground interference. Our own Milky Way's dust clouds or the solar system's motion could skew the data. But even after accounting for these factors, the signal persists, dangling the tantalizing idea that we're glimpsing something beyond our current physics. What makes this mystery so provocative is its scale. The axis of evil isn't some localized oddity. It spans the entire observable universe, a fossilized direction from the first trillionth of a second after the Big Bang. If real, it could rewrite our understanding of how the cosmos was born. Maybe inflation wasn't perfectly uniform. Maybe multiple Big Bangs left overlapping imprints. Or maybe, just maybe, we're staring at the smudged signature of a multiverse we'll never see. Until future telescopes like the European Space Agency's CMB-BHD mission probe these fluctuations with even finer precision, the axis remains a cosmic Rorschach test, a pattern that might reveal everything or nothing at all. Either way, it's a reminder that even the oldest light in the universe still has secrets to spill. Black holes have always been cosmic enigmas, but Stephen Hawking spotlighted one of their most baffling traits: their ability to erase information from the universe. This isn't just about matter vanishing beyond the event horizon. It's a fundamental paradox that strikes at the heart of physics itself. According to quantum mechanics, information can never truly be destroyed. Every particle state, every shred of data should theoretically be recoverable, like rewinding a cosmic film reel. But black holes defy this. When matter falls in, it's not just crushed, it's seemingly erased from existence, leaving no trace behind. Hawking's calculations suggested that black holes slowly evaporate over eons, emitting radiation that carries no information about what they've consumed. Poof, gone. That's the information paradox, a direct clash between quantum theory and general relativity, two pillars of modern physics that refuse to reconcile. For decades, scientists grappled with this problem. If Hawking was right, the universe would have a glaring loophole, a place where the rules break down entirely. But in the last few years, breakthroughs in string theory and the holographic principle have offered a glimmer of hope. The holographic principle proposes something mind-bending, that all the information swallowed by a black hole isn't lost inside it but encoded on its surface like a cosmic DVD. Imagine taking a three-dimensional object and flattening it into a two-dimensional projection without losing any details. That's the essence of this idea. The event horizon acts as a holographic storage device, preserving data in a form we don't yet fully understand. Recent simulations using quantum gravity models support this. When matter falls into a black hole, its information gets scrambled and smeared across the event horizon in an intricate quantum pattern. Over time, as the black hole emits Hawking radiation, that information leaks back out, albeit in a highly chaotic form. It's like shredding a document but leaving enough scattered fragments that, with infinite patience, you could piece it back together. The catch: the process is so complex and entangled that retrieving usable information is nearly impossible in practice. Yet this doesn't fully solve the paradox. The holographic principle remains a theoretical framework, not yet proven by observation. And even if it's correct, we still don't know how information makes the jump from inside the black hole to its surface. Some physicists speculate that space-time itself might be pixelated at the tiniest scales, with each pixel holding a discrete unit of data. Others suggest black holes could be gateways to entirely new universes, with information passing through like a cosmic fax machine. What's thrilling is that this isn't just an academic debate. The paradox forces us to rethink reality's deepest fabric, whether space-time is continuous or digital, whether the universe is deterministic or inherently fuzzy. And with experiments like quantum simulators and gravitational wave detectors, we might soon have tools to test these wild ideas. Until then, black holes remain the universe's ultimate shredders and its most tantalizing puzzles. Neutron stars are already cosmic oddities, stellar corpses so dense that a teaspoon of their material would weigh 1 billion tons on Earth. But among these extreme objects, magnetars stand out as the true freaks of nature. Picture a neutron star with a magnetic field 1,000 trillion times stronger than Earth, so powerful it could strip the data from every credit card on our planet from halfway across the galaxy. These magnetic monsters don't just sit quietly, they crack under the strain. That's right, magnetars experience starquakes, violent ruptures in their rigid crusts caused by unimaginable magnetic stresses. Think of it like this: the crust of a magnetar is a lattice of ultra-dense iron, squeezed so tight it's harder than diamond. But when the star's magnetic field twists and shifts, which it does constantly, it torques the crust until it snaps. The energy released in these fractures is staggering. A single magnetar starquake can unleash more gamma rays than the sun will emit in its entire 10 billion year lifetime, all in a fraction of a second. These explosions, called soft gamma repeaters, were first mistaken for distant supernova or even alien signals. Then, in 2004, a magnetar flare from 50,000 light-years away briefly ionized Earth's upper atmosphere, despite being halfway across the galaxy. If that eruption had happened within 10 light-years, it could have triggered a mass extinction. That's the raw power we're talking about. Here's where it gets even more fascinating. When a magnetar's crust cracks, the whole star rings like a bell, vibrating at frequencies that could theoretically produce gravitational waves, ripples in space-time itself. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. While LIGO primary targets are merging black holes and neutron stars, scientists are now tuning its instruments to listen for the subtler tremors of magnetar quakes. Detecting these signals won't be easy. Magnetar vibrations would be far quieter than the collisions LIGO usually hunts, buried in the detector's noise floor. But if successful, it would open a whole new window into neutron star interiors. The frequency and decay of these waves could reveal the exact thickness of the crust, the viscosity of the superfluid core, and even the nature of ultra-dense matter at pressures impossible to replicate on Earth. What's at stake isn't just understanding magnetars, it's testing the limits of matter itself. Under such extreme conditions, protons and neutrons might dissolve into a soup of quarks, creating states of matter that exist nowhere else in the universe. A gravitational wave fingerprint could be our first direct evidence. So while magnetas might seem like distant curiosities, their starquakes could hold the key to physics we've only dreamed of. And with LIGO listening, we might soon catch the echoes of these cosmic shudders, proof that even the most violent events in the universe leave whispers in the fabric of space-time. When theorists calculated how much lithium the Big Bang should have created, the numbers seemed rock solid. According to their models, the first 3 minutes of cosmic history forged not just hydrogen and helium, but trace amounts of lithium-7, an isotope that should still linger across the universe today. Yet when astronomers actually went looking for it, something didn't add up. The oldest stars, those pristine relics from the early cosmos, show only a third of the lithium expected. It's as if someone scrubbed 2/3 of this cosmic ingredient from the universe's recipe book without leaving a trace. The mystery deepens when you consider where lithium should be. Young stars like our Sun contain even less lithium than their ancient counterparts, suggesting some process actively destroys it over time. Picture a cosmic game of hide and seek where the hider keeps vanishing more thoroughly with each round. One leading suspect, stellar furnaces. When stars like the Sun churn their outer layers through convection, lithium atoms get dragged down to scorching depths where temperatures exceed 2.5 million degrees, hot enough to split them into helium. It's like tossing ice cubes into a blast furnace. They don't just melt, they cease to exist at a fundamental level. But that explanation only works for certain types of stars. Red giants, for example, should preserve lithium in their cooler outer layers, yet many show even more severe depletion. Then there's the twist. Some rare stars defy the trend entirely, boasting lithium levels 1,000 times higher than expected. Astronomers call these outliers lithium-rich giants, and their existence throws gasoline on the theoretical fire. If most stars destroy lithium, why do a few hoard it like cosmic dragons sitting on a treasure trove? One provocative idea involves stellar belches, violent mixing events where deep-buried lithium gets dredged up to the surface. Imagine a star's interior as a layered cocktail suddenly stirred by an invisible spoon, bringing long-lost ingredients back into view. Another theory points to cosmic cannibalism. When stars ingest lithium-rich planets or brown dwarfs, their atmospheres might temporarily spike with the missing element. Yet none of this solves the original puzzle of the Big Bang's lithium deficit. Could our models of the early universe be incomplete? Some physicists speculate that exotic particles like Action's hypothetical dark matter candidates might have altered nuclear reaction rates in those first fiery minutes. Others wonder if primordial black holes, tiny and dense, gobbled up lithium before stars could form. The stakes here are higher than just solving a cosmic accounting error. Lithium is a key piece of the puzzle for how the first stars and galaxies lit up the universe. If we've misjudged its abundance, we might be missing clues about the conditions that sparked the dawn of everything. And with next-generation telescopes like the extremely large thing set to analyze starlight with unprecedented precision, we might finally catch lithium's thief red-handed, or discover that the universe's ledger was never balanced to begin with. For nearly a century, astronomers have measured how fast the universe is expanding, a number called the Hubble constant. It should be straightforward. Pick a distant object, track its motion, and calculate the rate. But here's the cosmic curveball. Depending on where you look, you get two completely different answers. Measurements based on the early universe, like the cosmic microwave background, peg the expansion at 67 kilometers per second per megaparsec. Meanwhile, observations of nearby stars and supernova insist it's 73. That 6-kilometer difference might sound trivial, but it's tearing cosmology apart at the seams. This isn't just about a math error. The gap, known as the Hubble Tension, suggests something fundamental is missing from our understanding of reality. Imagine two detectives solving the same crime, one examining fingerprints at the scene, the other analyzing security footage and winding up with irreconcilable stories. That's where cosmology stands today. The early universe camp relies on pristine snapshots of the Big Bang's afterglow mapped by missions like Planck. These measurements are exquisitely precise, assuming standard physics holds true. The late universe team, though, watches dying stars called Cepheid variables and Type Ia supernova, whose brightnesses serve as cosmic yardsticks. Their numbers are equally rigorous, yet they stubbornly refuse to align. Enter the wild cards. Could invisible particles called dark radiation, fleeting relics from the universe's first second, be skewing the early measurements? These hypothetical particles, moving at near light speed, would have subtly altered how the infant cosmos expanded, leaving the 67 figure slightly off. Alternatively, maybe dark energy isn't constant but evolving, pushing galaxies apart faster than expected in recent eons. Then there's the nuclear option. What if gravity itself behaves differently over cosmic distances, forcing us to rewrite Einstein's equations? The stakes couldn't be higher. If the tension is real and not just systematic error, it implies 95% of the universe's dark matter and dark energy is even stranger than we thought. Future telescopes like the Nancy Grace Roman Space Telescope aim to settle the debate by measuring the expansion with 10 times the precision of Hubble. But until then, the Hubble tension remains the universe's way of keeping us humble, a reminder that even our best theories might just be rough drafts in the grand manuscript of reality. Somewhere in the constellation Boötes, there's a patch of sky so empty it defies logic, a spherical void stretching 330 million light-years across, containing almost nothing. No galaxies, no stars, just an eerie, near-perfect vacancy where astronomers expected to find tens of thousands of galaxies. They call it the Great Void, a cosmic anomaly so vast it could swallow our entire local supercluster without a trace. What makes the Boötes Void so unsettling isn't just its size, it's the sheer unnaturalness of its emptiness. Most cosmic voids are small, temporary bubbles, formed when galaxy clusters pull away from each other like drying paint. But this is a chasm that shouldn't exist under standard models of cosmic structure. Imagine pouring a handful of sand onto a sheet of paper and watching every grain somehow avoid one giant circle. That's the statistical improbability we're dealing with. So where did everything go? One theory suggests the void might be a fossil from the universe's infancy, an imprint of an ultramassive quantum fluctuation that left behind a bubble of near-nothingness when space first inflated. If true, the void isn't a hole but a relic, a preserved snapshot of the moment before matter existed. Others propose something darker, that the void is evidence of a collision with an alien universe during cosmic inflation, a scar left behind when another reality briefly brushed against ours. Then there's the wild card. Could something inside the void be hiding galaxies from view? One controversial study detected a handful of faint galaxies drifting in the void's depths, suggesting it might not be entirely empty, just emptier than anything we've seen. But here's the spine-tingling thought. What if those galaxies aren't natural? Some theorists have floated the idea of a Type 3 civilization, a Kardashev-scale superpower that's dismantled entire galaxies for energy, leaving behind an engineered wasteland. It's a fringe idea, sure, but when faced with a void this unnatural, even speculative answers feel worth considering. Yet the most haunting possibility is that the Boötes Void isn't special at all, and it's just the first of many such voids we'll find as our telescopes improve. If true, our maps of the cosmos might be riddled with similar blank spots, forcing us to rethink how structure forms on the grandest scales. Until then, the void remains a silent enigma, a reminder that emptiness itself can be the universe's most unsettling mystery. There's something haunting about stepping outside just before dawn or after dusk and catching a faint, ethereal glow stretching up from the horizon, a pale, triangular light that seems too delicate to be real. This is the zodiacal light, sunlight scattered by countless dust particles drifting through the inner solar system, But here's the cosmic head-scratcher: there shouldn't be this much dust here. Not this close to Earth, not after billions of years of planetary formation and gravitational housecleaning. So where's it all coming from? The leading theory points to the asteroid belt, where collisions between rocky bodies, some as small as pebbles, others as large as mountains, grind each other into fine powder. Every time two asteroids slam together, they release a fresh spray of debris, some of which gets nudged inward by sunlight's gentle push. Over millennia, this dust spirals toward the sun, creating a shimmering cloud along the plane of the solar system. But calculations suggest this process alone can't account for the sheer volume of dust we see. There's too much of it, too close to home, like finding a snowdrift in the desert. That's where comets enter the picture. These icy nomads barreling in from the solar system's frozen fringes shed colossal amounts of dust as they melt near the sun. A single comet like Hale-Bopp can leave behind billions of tons of debris in its wake. But even this doesn't fully solve the puzzle. Modern surveys show that while comets contribute, their dust tends to disperse widely over time, not concentrate neatly along the zodiacal plane. Then there's the wild card, Mercury. Recent simulations suggest the sun's scorched closest planet might be kicking up dust itself. Meteoroid impacts on Mercury's surface could launch particles into orbit, where solar radiation pushes them into the inner system. It's a provocative idea. A planet we thought was too small and dry to contribute meaningfully might actually be a silent player in this cosmic dust storm. But the real twist: some of this dust might not be ancient at all. In 2021, Japan's Hayabusa 2 mission found tiny particles on asteroid Ryugu that matched the composition of zodiacal light dust, except they were far younger than expected. Instead of being leftovers from the solar system's birth, some grains appeared freshly broken off, as if the asteroid belt is still actively crumbling. If true, it means the zodiacal light isn't just a relic, it's a living phenomenon fed by ongoing celestial demolition derbies. What's mesmerizing is how this delicate glow ties together the solar system's violent past and present. Every photon of zodiacal light we see is a message from a collision that happened millions of miles away, a whisper of chaos rendered beautiful by distance. And with missions like Europe's Comet Interceptor poised to study pristine comets in the coming decade, we might finally crack the case of where all this dust is coming from, or discover it's been hiding in plain sight all along. Beyond Neptune's orbit, where sunlight is little more than a faint star in the darkness, lies a ring of icy debris called the Kuiper Belt, a cosmic junkyard holding leftovers from the solar system's formation. Most of these frozen worlds orbit quietly, but astronomers noticed something bizarre when they mapped their distribution. Suddenly, around 50 astronomical units out, that's 50 times the Earth-Sun distance, the Kuiper Belt just stops. It's not a gradual thinning like a fading echo. It's a hard edge, as if someone drew a line in the cosmic sand and said, "Nothing allowed past this point." This invisible boundary, known as the Kuiper Cliff, makes no sense under current models. The belt should continue smoothly for hundreds more astronomical units, its population dwindling slowly with distance. Instead, it's like walking through a forest that abruptly ends at a sheer drop-off. So what's cutting off the supply of icy bodies? One tantalizing possibility is that an unseen planet, larger than Earth but smaller than Neptune, is lurking beyond the cliff, its gravity clearing out debris like a cosmic snowplow. The idea isn't as far-fetched as it sounds. We've seen similar shepherding effects before. Neptune's gravity sculpts the inner edge of the Kuiper Belt, keeping orbits orderly. But a hidden world beyond 50 could explain the sharp cutoff. Dubbed Planet 9 by some researchers, though it's distinct from the hypothetical super-Earth proposed to explain distant object orbits, this stealthy giant would be frigid and faint, reflecting almost no sunlight. That's why even powerful telescopes like Subaru and the Vera C Rubin Observatory have yet to spot it, yet not everyone's convinced a planet is the culprit. Alternative theories suggest the cliff might be a scar from the solar system's violent youth. Picture this: billions of years ago, a rogue star passed uncomfortably close to our newborn system, its gravity yanking away everything beyond a certain radius. Or perhaps the early sun was born in a dense stellar nursery, where neighboring baby stars stole material from our outer reaches. Either scenario could have left behind a Kuiper belt with a sudden, unnatural edge. Then there's the wild card. What if the cliff isn't real at all? Detection bias could play a role. Smaller Kuiper belt objects beyond 50 might simply be too dim for our current surveys to spot. New Horizons, now venturing deeper into the Kuiper belt, could settle the debate if it stumbles upon a population of hidden, far-flung objects. But until then, the cliff remains one of the solar system's most puzzling boundaries, a silent enigma at the edge of everything we know. Whether it's an unseen world, an ancient theft, or just a trick of the light, the Kuiper cliff forces us to confront how little we truly understand about our own cosmic backyard. And with every new mission and telescope, we're peeling back another layer of this frozen mystery, inching closer to whatever or whoever drew that line in the first place. Every story has an ending, but when it comes to the universe, the final chapter is still being written. Will space expand forever, chilling into an eternal graveyard of scattered particles? Or will gravity eventually win, reversing the Big Bang in a fiery collapse? Or could the cosmos be caught in an endless cycle of rebirth, where every ending births a new beginning? These aren't just thought experiments, they're competing visions of reality itself, each with staggering implications for how we understand existence. Let's start with heat death, the bleak but leading contender. Picture a universe where expansion never stops, where galaxies drift so far apart that their light can never reach one another again. Stars burn out, black holes evaporate, and matter itself decays, protons crumbling over unfathomable eons until nothing remains but a thin, frozen haze of particles too distant to interact. It's the ultimate thermodynamic equilibrium. No energy differences, no motion, no change. Just a silent, infinite fade to black. This isn't science fiction. It's the inevitable outcome if dark energy keeps accelerating the cosmos unchecked. And given current measurements, it's the most likely fate we've got. But what if gravity fights back? Enter the Big Crunch, a dramatic counterpoint where expansion slows, halts, and ultimately reverses. Imagine all the universe's matter rushing back together, galaxies merging into a cosmic traffic jam of collapsing space. Temperatures soar as atoms are ripped apart, space-time warps beyond recognition, and everything, every particle, every law of physics compresses into a singularity. Some theories even suggest this singularity could trigger another Big Bang, a cosmic reset button. The problem: observations show expansion isn't slowing, it's speeding up. Dark energy seems to have the upper hand. Unless something changes, the crunch might remain a tantalizing what if. That's where Roger Penrose's audacious conformal cyclic cosmology comes in. He proposes a universe where the distant future becomes another Big Bang, not through collapse but through transformation. In this model, as the universe approaches heat death, all particles lose mass due to quantum effects, effectively erasing time and scale. What's left is a smooth, empty canvas indistinguishable from the pre-Big Bang singularity. A new eon begins, echoing the last. It's a poetic idea, no true end, just an infinite series of universes, each unaware of the ones before it. Critics argue Penrose's theory relies on speculative physics, but his claims of Hawking points, anomalies in the cosmic microwave background that could be echoes of previous eons, keep the debate alive. What's fascinating is how these theories reflect our deepest questions about time, existence, and meaning. Heat death implies a finite story with an irreversible finale. The Big Crunch offers cosmic rebirth, but at the cost of total annihilation. Penrose's vision, an endless, unknowable loop where every ending is a beginning in disguise. For now, the universe keeps its ultimate secret, but with every new telescope and quantum theory, we're inching closer to reading the last page, and who knows? The truth might be stranger than any of our predictions. Consider for a moment that our universe might just be one page in an infinite cosmic library, a single reality among countless others, each with its own laws, its own history, maybe even its own version of you. This isn't science fiction, it's the multiverse hypothesis, a radical idea growing out of quantum mechanics and cosmology. At its core is quantum branching, the notion that every decision, every random event, splits the universe into parallel timelines. Did you turn left today instead of right? Somewhere out there, another you went the other way. Physicists call this the many worlds interpretation, where reality isn't a single thread but a sprawling tapestry of possibilities. But the multiverse isn't just about alternate versions of Earth. Some theories suggest entire universes could exist with different fundamental constants, places where gravity is stronger, light slower, or where atoms never formed at all. Imagine a cosmos where the laws of physics are so alien that time flows backward or space has 11 dimensions. These aren't just thought experiments, they're potential solutions to fine-tuning puzzles. Why does our universe seem perfectly calibrated for life? Maybe because we're just one lucky roll of the dice in a sea of failed realities. Then there's the holographic principle, a mind-bending twist suggesting our three-dimensional universe might be a projection from a two-dimensional surface at its edge, like a cosmic version of a credit card hologram. Black holes hint at this. The information swallowed by them seems to be encoded on their event horizons, not lost inside. Scale that up, and the entire universe could be a hologram, with reality as we know it just a shadow of deeper, more fundamental processes. But if that doesn't unsettle you, meet Nick Bostrom's simulation argument. The philosopher's trilemma goes like this. Either civilizations never reach the technological capability to simulate conscious minds, or they do but choose not to, or here's the kicker, we're almost certainly living in one of those simulations. Think about it. If advanced civilizations can create ancestor simulations with sentient beings inside, the number of simulated minds would dwarf biological ones. Statistically, the odds tilt heavily toward us being lines of code in some supercomputer. Critics push back maybe simulations can't perfectly replicate quantum randomness, or perhaps the energy costs are prohibitive. But the deeper question remains, if reality is a construct, does it matter? The sensations, the struggles, the starlight we see, it all feels real, and that might be the most haunting thought of all. Whether we're one universe in a multiverse, pixels in a hologram, or characters in an alien's video game, the mysteries we chase might just be layers in an even grander enigma. We've traversed the cosmic horizon, from the ghostly pull of dark matter to the eerie silence of the Fermi Paradox, from black holes that erase reality to Martian methane that flickers like a cosmic Morse code. These aren't just puzzles, they're reminders that the universe is a master of misdirection, dazzling us with answers that only lead to deeper questions. Every discovery peels back a layer, revealing new mysteries beneath. Take dark energy, hurtling galaxies apart faster than gravity can pull them together. Or the axis of evil, a cosmic fingerprint that shouldn't exist, hinting at a universe with a hidden preference. Even our own solar system guards secrets, like the Kuiper Cliff's razor-sharp edge or Venus's phosphine-laced clouds, where the line between chemistry and biology blurs. And let's not forget the wow signal, a 72-second scream from the void that still haunts astronomers decades later. The beauty of these mysteries isn't just in their complexity, it's in their audacity. They defy our expectations, refusing to fit neatly into textbooks or equations. But that's the thrill of exploration. Every unanswered question is an invitation, a cosmic dare to look closer, think deeper, and dream bigger. And we're not done searching. The James Webb Space Telescope is already rewriting the playbook, peering into the atmospheres of distant exoplanets and capturing light from the universe's first galaxies. Upcoming missions like Europa Clipper and Dragonfly will probe alien oceans and methane rivers, while gravitational wave detectors listen for the tremors of colliding neutron stars. The next great discovery might be lurking in tomorrow's data, waiting to append everything we thought we knew. So tonight, step outside, look up, let your eyes adjust to the darkness, and remember, every star, every flicker of light is part of a story we're only beginning to read. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and the best part, this cosmic mystery show has no final curtain. The next act is always just beyond the horizon. What do you think we'll find next?